Hello Pharma aspirants, welcome to Target Pharma 360 degrees. That means the MCQ series we have started in our GDC English channel, right? So in this we are going to discuss n number of the MCQs which are going to be helpful for you in cracking the competitive exams like MRB, RRB, GPAT, NIPER, Pharmacist, AIIMS, all these exams, okay? So let us start our today's session, which is mainly dealing with the MCQs related to the atomic absorption spectroscopy. Okay, so this atomic absorption spectroscopy MCQs majorly these are going to be based on the instrumentation part as well as the mechanism. Okay, so how this technique it is going to be helpful and what are the different elements which are going to be estimated by this technique. So let us see the first question involved in this atomic absorption spectroscopy. First of all, you should know the difference between atomic absorption and atomic emission. Okay, so the first question is related to the atomic emission spectroscopy. They are asking. So in this, what is atomic emission spectroscopy? So atomic emission spectroscopy, if you observe the options, let us see. The measurement of intensity of the emitted light. Emission spectroscopy, that means automatically emitted light only at a particular wavelength from the atoms that are excited thermally. So by looking wise the statement looks correct. And let us see the another options. The measurement of absorbance of the emitted light at a particular wavelength from the atoms that are excited thermally. Oh, actually here they are giving intensity of the emitted light, whereas here they are giving absorbance of the emitted light. No, actually for the emitted light means we are not going to take the absorbance. Emitted light means we are going to, in terms of the intensity only, we are going to measure that, right? Third, the measurement of intensity of the emitted light, okay, relevant to this, at a particular wavelength from the atoms that are excited by monochromatic light. No, nowhere monochromatic light we are going to use it, but that is not the correct way. Okay, thermally we are going to excite the first of all the atoms, and lastly if you see the measurement of intensity of the absorbed light at a particular wavelength from the atoms that are excited thermally, not the absorbed light. This is going to be absorbed light means atomic absorption spectroscopy, but here what they have asked the question, atomic emission spectroscopy. So obviously if you see the correct option, that is nothing but the first one, the measurement of intensity of the emitted light. Okay, in the emission spectroscopy means intensity of the emitted light we are going to measure, which are already thermal excitation, it is going to be given to the atoms. Next question, if you see the most widely used flame in the atomic absorption. Okay, what is the flame? Because we know that in the atomic absorption spectroscopy, hollow cathode lamp it is going to be used first of all source, and whenever we are going to use it for the specific elements like sodium, calcium, specific hollow cathode lamps are going to be used, and from that the electrons are going to be generated. Okay, so these are going to be taken up into the flame, right? So that in order to generate that flame, what is the widely used flame? So by mixing the fuel with the oxidant we are going to get the flame. So here they have given some of the options. The widely used flame: air coal gas, air propane, air acetylene and oxyacetylene. So let us see first of all what are the different temperatures we will get with the different fuels and oxidants which are available for using this atomic absorption spectroscopy. Okay, so natural gas and air if you take, you are going to get up to 1840 degrees centigrade, and propane and air if you take 1900 around, hydrogen and air means 2100 around, acetylene and air you are going to see the 2250 degrees centigrade. Okay, and this is going to be the most widely used a fuel and oxidant ratio for most of the compounds in this AAS technique. Hydrogen and oxygen 2700. So increasing the temperature, if you are going to observe, natural gas with oxygen 2800 around, and propane with oxygen it is going to plus 2850 plus it is going to give, and acetylene and oxygen you are going to get it above 3100. Okay, so these are the different air acetylene oxidant and fuel mixtures you are going to get it, but widely used mixture, that is acetylene and air. Okay, so this combination we are going to use it for most of the elements. So C, it is going to be the right option here. And the third question, if you observe in atomic absorption, chopper. Okay, so in the instrumentation part we are going to use the hollow cathode lamp, as well as in between the flame we are going to put the chopper there. So what is the purpose of the chopper? So here they have given to measure the concentration of the elements, to measure the wavelength of the light emitted by the substance. No, chopper and wavelength, these are not at all related. And third option, to break the steady light into the pulsating light. Yes, this is going to be the right answer. Fourth one, to measure the radiation from the source. No, that is not the source. So obviously if you see the right option, it is going to be the steady light into the pulsating effect. So before answering that, let us see what is the purpose of this chopper. Actually, if you are going to observe this hollow cathode lamp, from that you are going to take the source. Okay, that means from that this cathode, it is going to generate the electrons whatever for the required element, and here in between the flame and the lamp we are going to place this chopper. Okay, so chopper, it is going to be placed once in the open condition and second in the mirror condition. So open condition, if you are going to put it, the chopper, means the light, it is going to pass through the flame. Okay, so thereby it is taken up by the sample, as well as then all this integration absorption, it is going to take place, and we are going to see the graph there. And whenever we will put this chopper in the mirror condition, what happen? It is going to reflect this radiation towards it, because it is actually double beam optical bench atomic absorption spectrophotometer. So then what happened? The radiation, it is not passing through this flame, it is going to be traveling like this, and it is reaching the detector. Then what happens exactly? So if you change the chopper position, one into the flame and other into the as a mirror, if you are going to reflect that radiation, then exactly what happens means the chopper here alternates between the two optical paths here, and one in which the light from the hollow cathode lamp bypasses. This is what happening. It is going to be the light radiation whatever falls on it. So when it is kept in the mirror position, what happened? It is going to bypasses the flame. It is not entering the flame here. Okay, and that measures the total emission. The total emission which has been generated by this lamp, it is going to be taken up by this, okay, detector. It is monochromator, then it is going to be taken up. So when we put this chopper in the mirror place, then what happened? Whatever the radiation it is passing through the flame, it is taking. So thereby the difference you are going to take, what is the amount of the light it has been absorbed by the certain particles or certain elements. Okay, so in that way chopper, it is going to be helpful for us. And third question, if you see in atomic absorption spectroscopy, chopper it is used. Again, yeah, the same. Okay, so the same question till now we have seen that. So with the chopper, what we are getting? The total minus absorbed light. So whatever the not absorbed, it is going to be there. Thereby you are going to get the exact absorbed radiation you are going to see. So to break the steady light into the pulsating light. So this is also one of the advantage. So whatever the steady light it is there, it is just passing through the flame, means it may not be completely absorbed. So in order to create the pulses, where this chopper, it is also going to be helpful. Okay, next, fourth one, source of light used in the atomic absorption. Just now we have seen in the picture also, hollow cathode lamp, it is going to be used as a source of radiation in the atomic absorption. So hollow anode lamp, no, cathode lamp, right, hollow lamp, filter wheel. Okay, so option B, it is going to be the right answer. Next question, in atomic absorption spectroscopy, chopper is used for, just now we have seen the chopper, it is used for the breaking the steady light into the pulsating light. Okay, so one more uses for this chopper, let us see. To measure the concentration of the elements, no, not at all. To measure the wavelength of the light emitted, no. To measure the intensity of the light, yes, total emission of the light, whatever it is there. Okay, so the intensity of the light which is absorbed by the elements, exactly if you want to know means shopper it is going to be helpful. Next, to measure the radiation, no, not at all. So option C it is going to be the right answer. Okay. Next question, the theory of nebulization. Okay, whenever we want to input the sample in this atomic absorption spectroscopy, we are going to use a nebulization process. Okay, so in order to theory of nebulization is associated with in which technique? Nephelometry, atomic absorption spectroscopy, AAS, fluorimetry, titrimetry. So in the AAS only we are going to use the nebulization process in order to spray the sample into the flame. Okay, so nebulizer is highly going to be helpful in order to make the solution into the uniform manner, and directly into the flame also we can incorporate the sample, okay, without any wastage. So next, mercury in the thiomersol, okay, the sample solution, that is thiomersol, which can be detected by using the which type of the technique, in which technique mercury can be detected. That means mercury means it is an element, and at the atomic level we want to determine means definitely at the atomic spectroscopy it is useful. And if you observe in this case fluorimetry, IR, UV visible, all these three are going to be estimated at the molecular level. Okay, total entire molecule we are going to determine by these three techniques, whereas atomic absorption spectroscopy it is atomic orbitals, atomic at the excitation ground state the atoms are going to be involved in this atomic absorption spectroscopy, right. Next, zinc in the zinc insulin injection is detected by which technique? Zinc, especially the element, whenever you are going to use the in the injection by total in zinc insulin injection, if you want to estimate the zinc only means what is the technique you are going to use here? Flame photometry, atomic absorption, IR spectroscopy and fluorimetry. Only the elements can be estimated by this atomic absorption spectroscopy, because it is going to absorb the radiation. Okay, so if it is having the emission properties, then you are going to observe it in the flame photometry, but zinc mostly you are going to see the absorption spectroscopy. Okay. Next, which of the following spectroscopy is temperature dependent? Okay, so according to the temperature, already we have seen different fuel and oxidant ratios are also giving different temperatures. So definitely you can say that atomic absorption spectroscopy is temperature dependent. Okay, and fluorimetry, flame photometry, IR spectroscopy, these are also temperature dependent only, but even though not much wide variation it is there. Okay, that means if you perform a 20 degrees and 25 degrees centigrade also, IR spectroscopy is not varying results you are going to observe, not much variable results you are going to see in this case, whereas fluorimetry, flame photometry also you are going to see the same type of the conditions there. But whereas atomic absorption spectroscopy means by changing the temperature of the flame, fuel and oxidant ratio, high temperatures and low temperatures, you are going to see different atomization process also. Okay, so that's why C it is going to be the right answer. Next question, if you see the determination of the lead, okay, elements and metals, if you are going to see lead in the petrol is analyzed by which of the following technique? Flame photometry, atomic absorption, fluorimetry and IR spectroscopy. It is a liquid petrol means you are going to take that solution, and as well as lead hollow cathode lamps are also available. You can estimate by this atomic absorption spectroscopy. This is also one of the application. Okay, and hollow cathode lamp is used as a light source. So we know very well the very simple question. So in the atomic absorption spectroscopy only hollow cathode lamp is used. Okay, so remaining techniques, flame emission spectroscopy, UV visible, ESR, so these are not related to this hollow cathode lamp. Okay, so flame emission means again you are going to take the flames, we are going to be taken as a source of radiation there. Okay, and UV visible means deuterium lamps are going to be used as light source. Electron spin resonance means there we are going to use the radio waves. Okay. Next question, if you observe which type of the interferences are absent in the atomic. Generally, what are the interferences are going to be observed due to the elements in the spectroscopy means mostly they are going to be observed in this AAS only, atomic absorption spectroscopy. But here what they have asked, which are not observed in this atomic absorption. Anionic interference, cationic interference, background and ionization. First of all, let us know and then we will come to answer this question. Okay, let us know first what are the different types of the interferences generally which we are going to observe in this atomic absorption spectroscopy. Means whenever a particular element it is present like zinc, lead, mercury, okay, at the atomic level we want to estimate, means some of the other elements are also going to interfere. Okay, such interferences may cause some of the other problems. Let us see what are those type of the interferences. First of all, if you categorize those interferences, spectral interferences, second one ionic interferences, third one chemical interferences. Okay, spectral interferences, if you are talking about whenever the emission lines, okay, so because of the absorption only it is going to be there, but whatever the emitted lines are there, so whenever the two elements are present, so which are not going to be resolved, okay, that means they cannot be separated, or which can be arise from the background of the flame itself. But background of the flame itself means sometimes we need to correct it. Background correction methods are also available. So from that background correction can be done. Okay, but whenever two elements are present, spectral interferences are going to observe which can overlap. Either these are going to be too close or overlap. Okay, so because of the why these spectral interferences are going to occur, that means because one or more elements are going to be present in a same sample, as well as these are going to be present at the high concentration of the salts are going to be present in that. Okay, so that's why you are going to see the spectral. And coming to the ionic interferences, high temperature flame, whenever those fuel oxidant mixtures are there. Okay, so high temperature flames we are going to use more than 1800, 1900, 2000 degrees centigrade. So they may cause ionization of the some of the metal atoms. Ionization it is going to occur. As such metal we cannot estimate. Sometimes that temperature it is going to cause the ionization. Like sodium. Sodium we know that as such sodium we can estimate, but if you use the high temperature, okay, so more than 2500 like that, it is going to cause the ionization like sodium plus it is going to form. So the spectra for the sodium as well as sodium, ionized sodium, it is going to be completely different. So in order to avoid this, what we have to do, some suppressors are required in order to suppress the ionization. Okay, so you need to maintain the suppressors, okay, ionization suppressors you need to add, thereby you can avoid this problem. And sometimes the temperature, okay, so in order to slow down this ionization, what we have to do, that means high temperature flames should not be used for such samples. That is also one of the remedy we can do. Next, chemical interferences. Chemical interferences means whenever the in between the different chemical compounds are there, you are going to see the, so definitely two interferences are present, then one of the chemical may react with the other. Okay, so these chemical interferences are going to be either one of the following, like cation anion interference, cation cation interference, and oxide formation interferences are also there. That means most of the ions, most of the elements which we are going to be estimated by this atomic absorption are going to be cations only. Okay, so whenever these anions such as oxalates and phosphates, sulfates, all these present in the solution, they may interact with these cations. Okay, those interferences are called as cation anion interference. For this, the best example is calcium and phosphate. Whenever calcium it is going to be in the plus state, okay, whenever we want to estimate this calcium, automatically phosphate ions, so if these are present, then they are going to form a calcium phosphate, which is a highly stable compound which cannot decompose very easily. Okay, so that's why the interference it is called as cation anion interference. And cation cation interference means mostly between two same type of the cations, like aluminum interferes with the calcium and magnesium. Okay, so all these three are cations only, so they may get interfere like this. And oxide formation interferences, magnesium oxide, okay, calcium oxides are also at the high temperatures, you are going to see the oxide formations, thereby you are going to observe all these types of the interferences. So these interferences are going to be present in the atomic absorption, but background interference we can correct that. Okay, so that's why if you see this question for this which cannot be, that means which are absent, that means background corrections are going to be absent, that means we can correct that background correction, background interference. Okay, so that is the meaning. But anionic, cationic and as well as ionization interferences are going to be present. Okay, that means all the cationic and anionic interferences are also going to be present, but sometimes background corrections, if these are present also, we can eliminate them, right? Next, excitation light source in the atomic absorption spectrophotometer. That means what is the source in order to excite the ground state atoms in this AIS? It is nothing but deuterium lamp, mercury lamp, xenon lamp, hollow cathode lamp. Oh my god, hollow cathode lamp has at least 4 to 5 questions in this series. Okay, option D, it is going to be the right answer. No need to again discuss. Next, atomic absorption is a type of absorption at the atomic level. We are going to define. First one, molecular spectroscopy. No, not at all. It is going to happen at the atomic level, and it gives the line spectra. Molecular spectroscopy and gives the band spectra. Atomic spectroscopy and gives the line spectra. Atomic spectroscopy, it gives the band spectra. Okay, that means how the emission lines are going to be observed. In this means actually it is not like a band, it is simple lines we are going to get it. So that's why C, it is going to be the right answer. Okay. And next question, if you observe, what the determination of sodium through this atomic absorption spectroscopy, what is the coating of the cathode? So whenever hollow cathode lamp it is used, it is specific for the element, means the same coating cathode lamp should be used. If you are going to use the sodium element, that means sodium coated cathode lamp we have to use. If you are going to use the magnesium, determination of the magnesium is going to be done, means hollow cathode lamp on which magnesium coating has been done. The same type of the hollow cathode lamp it is required. So in this question they have asked sodium, they are going to estimate by the atomic absorption. That means the cathode lamp should be coated with the sodium only. Okay, so iron, sodium, calcium, copper, definitely option B, it is going to be the right answer. Next, choose the process during the atomization in the atomic absorption. That means the sequence of the process, how these are going to be, the process it is going to occur. Desolvation, nebulization, dissociation, volatilization and ionization. Actually, whenever we are putting the sample, first of all the nebulization, the nebulizer will take the sample. So first of all the nebulization it is going to occur. So obviously if you see the nebulization in these two options it is there. So let us see how this nebulization, afterwards volatilization. No, immediately it is not getting volatilized. First of all, in the atomization process what happens is, that is desolvation. Whatever the solvent particles are there, okay, they are getting desolvated from the solute. Afterwards those solvent particles are going to be vaporized. So that's what that is called as volatilization. Okay, so here nebulization is correct, but in this volatilization and desolvation, these two are reversed. First of all desolvation occurs, then volatilization, then dissociation, or finally ionization it is going to occur. Okay, so this is a C, it is going to be the right answer. Next, destruction of the sample occurs in which spectroscopic method? That means sample gets totally denatured. No, and one more time, you cannot use that sample, completely gets denatured of the sample. What is that destruction? NMR, IR, atomic absorption and UV. NMR means you are going to prepare a solution, you are going to put it in the instrument, means again if you want to do that, means radio waves, whenever these are going to passing through that sample, it is not getting denatured, or it is not destructing that. Okay, so NMR, it is not the right answer here. IR sample, you can many times you can analyze, no destruction of the sample it is going to take place, it is just causing the transitions in the molecule. Okay, whereas atomic absorption spectroscopy, complete ionization it is going to take place. Once the sample has been placed into the flame, means the denaturation or destruction of the sample it is going to take place, right? So that's why C, it is going to be the right answer. And in the UV also, somehow you are putting the solution, once the UV rays are going to pass through the sample, means the sample gets absorption of that UV light. Okay, but here there is no destruction, But even though there is no destruction, you cannot reuse the UV sample again for the analysis. Once the UV rays has been passed through the sample means that is done. You cannot reuse that. That you have to remember that. Okay. But destruction, it is not going to take place. In the sterilization process means, okay, UV light is going to be used as a good sterilizing agent, but complete destruction, it is not going to take place in the UV. Okay. Next, the basic principle of AIS. Okay, principle involved in this atomic absorption spectroscopy. Let us see the options. Absorption of the radiation by the free atoms in the ground state. Yes, right. Free atoms, whenever ground state are there, then we are giving the energy, that means excitation will take place. Emission of the radiation by the excited molecules. No, emission is not going to be taken. And scattering of the light, no way. Absorption of the radiation by the ions only. Oh, no. Absorption of the radiation by the atoms, actually it is going to take place, not by the ions. Ions finally they are going to form. So obviously A, it is going to be the right answer. Next question, an AS, atomic absorption spectroscopy, chemical interference can be minimized. So already interferences we have discussed, spectral interferences, ionic interferences, chemical interferences. So these chemical interferences, how we can minimize? Cation, 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 anion, okay, oxide formation. Let us see the options. Adding releasing agents, lowering the flame temperature, using wider slits, removing the chopper. Actually, lowering the flame temperatures, we can minimize the ionic interferences. Using wider slits means we can increase the intensity of the radiation, but we cannot minimize the chemical interference. Removing the chopper means there is not a specific exact absorption you cannot measure, okay, and pulsating effects also you are not going to get it if you remove the chopper. Only the option that is adding releasing agents, that means these cationic, anionic or any type of the ionic anion, cation, all these interferences are going to occur because of the different chemicals only. So by adding such releasing agents, we can reduce these chemical interferences. Okay. Last question, if you see in atomic absorption spectroscopy, the function of the monochromator. Okay. So after the flame, if you see the monochromator, it is going to be present. Wherever you are going to see the monochromator, it is the purpose of the monochromator only. It is converting polychromatic to the monochromatic. That means here let us see the options. To isolate a narrow wavelength from the source of radiation, definitely it is the right answer. To increase the atomization efficiency, nowhere. Atomization and monochromator efficiency cannot be there. To produce a continuous radiation, to detect the fluorescence. So obviously option A, it is going to be the right answer. No need to discuss the other three options. Nowhere these are going to acting in the case of the monochromator. Okay. So these are few MCQs related to this atomic absorption spectroscopy. So more such MCQ series, so please watch the videos which are going to be daily uploaded on our GDC English channel. Okay. Thank you students. Thank you for attending.